Okay, so now we are continuing on looking at our reverse bias circuit, and we're going to see if we can figure out what the current is in this case. So it's hooked up in reverse bias. Our diode is reverse bias now. So what we're anticipating is basically no current, something that's going to be very, very small. All right, so we have our voltage source here, and that's our positive end, and we've got our diode hooked up in that orientation, which is reverse bias, because we have this bar end that would be connected to through that resistor to the positive end of the voltage source. So we can do basically the same analysis. So if we draw this circuit off to the side and say that it's now a fixed voltage source at Vs equal to 25 volts, we have a resistor R, and this value has changed. It's now 1 megohm. So that's a much larger resistance than 1 kiloohm. 1 megohm. Oops. Ohm symbol. So we have our diode in reverse bias. Current's going to try to flow through in this direction. And what we measure, and we'll just say that we measured this in a lab, and we found that VR, and we're using VR here to indicate reverse bias voltage, not resistor voltage, but the reverse bias voltage of the diode, is 24.97 volts. Okay, and since this is now being indicated VR for reverse bias diode voltage, we'll say that this is R1, and this voltage across the resistor is VR1. Okay, because we have to have some voltage drop there as well. All right, so we're using the same general approach. This is KVL, and this is Ohm's law. Ohm's law. So KVL is used to find this relation right here. And this is the voltage source minus the diode voltage. And that will leave us with, using Kirchhoff's voltage law, that will leave us with this voltage right here. So what we're really doing is just using Ohm's law to find current through the circuit by dividing the resistor voltage by the resistor value. Okay, so if we're going to find this resistor voltage by subtracting the reverse bias diode voltage from the source voltage, compare these two numbers, we have 25 volts applied, and we have 24.97 volts across that diode. So obviously the vast majority of the voltage is being dropped across this reverse bias diode. And that kind of matches up with our current understanding of reverse bias diodes, because they essentially act like an open circuit, right? So if we have an open circuit, all of that Vs is going to be across that open circuit. However, there's a little bit of a difference when we actually use a diode, because there is that very tiny reverse bias current that can flow through. So that's why we're going to see a little bit of a voltage drop, and it's not exactly like having an open switch. Okay, so we're using the same general idea here, and we're going to see just how small that current actually is in this situation. So using that formula, we've got that 25 volts for Vs, subtracting that 24.97 volts for the reverse bias diode voltage. This whole thing is giving us the voltage across the resistor, and we divide by the value of the resistor. And what we get is this very small current value, 30 nanoamps. So that's 30 times 10 to the minus 9 amps. Okay, so it's a very small current, which is why we basically say that there's zero current flow when we have a diode hooked up in reverse bias. So it essentially acts like an open circuit. Okay, so this is Shockley diode equation. I'm going to kind of skip over that if you were going to continue with this stuff, or if you're going to look into electrical engineering classes, that would be much more important. So I'll just skim over it for now. And it's going to bring us to the ideal diode model. So there are a couple different diode models that we're going to look at. This is the first one. It's treating it as an ideal component. It's going to be the simplest model. And it's going to give us two different models for forward versus reverse bias. And this is going to be how we're going to analyze these simple circuits. So looking at the diode's behavior when it's forward biased, first, we just look at the circuit. We see, all right, here's the positive end of the voltage supply. Here's how the diode is hooked up in the circuit. Current is going to try to flow through in the direction of the diode arrow. So this is forward bias. And since we've identified this as forward bias, this would be how we model that circuit. We model this diode as a switch. So it can either be on or off. And in forward bias, we simplify this and say, in forward bias, current flows to the diode. So I'm just going to say that the diode acts like a closed switch. If we have a closed switch, that acts like a short circuit. So a closed switch acts like a short. And across a short, that's just a wire. So there's no resistance and there's no voltage drop. No resistance, if we remember E equals IR, Ohm's law, if we have an ideal wire that has 0 ohms of resistance, doesn't matter what that current is, we're multiplying it by 0 ohms. So our voltage is going to be 0. We have 0 volts across a short circuit, across a piece of wire, across a closed switch. So since we're modeling our diode as a closed switch, we're going to have 0 volts across it. So that means what we basically have for this circuit here, this is our voltage source, our resistor, and our diode is now just a wire. This is where our diode used to be, and it's just a wire. So all we really have is this Vs and R in the circuit. So if we want to find current, our current is just going to be Vs divided by whatever that value of R is. And that's what we have right here to find the diode current. Okay, so ideal diode model, if our diode is in forward bias, it's modeled as a closed switch, which means that our diode current can be found just by taking Vs divided by R. Okay, so that's the first one. And then if we're looking at the reverse bias situation in the ideal diode model, first we just identify that this diode is hooked up in reverse bias, so we want to find out what the diode voltage and the diode current are going to be. That's our objective for this in general. So in reverse bias, we simplify and we say there's no current that's going to flow through, so our diode is going to act like an open switch. So this is acting like an open, and in an open circuit, whatever voltage is across here has to be equal to the voltage source. It's going to not have any voltage dropped across this resistance, because compared to the infinite resistance, basically, of an open circuit, this is a very, very tiny negligible resistance. So all of that voltage is going to be dropped across the open right here. So this diode voltage, reverse bias diode voltage, is going to be equal to Vs. And then, since this is a broken circuit, right, this is open, there's no complete path for current to flow anymore, so our current is just going to be 0. So when we have our closed switch, voltage is 0. When we have an open switch, current is 0. Okay, so this is our basic idea for the ideal diode model. And then if we look down here, exiting annotation mode here, we can see a simple example. And I would suggest that you guys take a quick look at those. But I'm going to pause this one just for right now so we can break this up into another video.